This is the second section of chapter 8, which is modelling with differential equations. And here we're going to be looking at simple harmonic motion. Now, probably if you've never met simple harmonic motion before, probably just a quick explanation of what it looks like. So let's imagine like a pendulum. And so a pendulum's this sort of thing where we've got like a weight on the end of a piece of string. So imagine we've got a piece of string, so it goes down like this, and we've got a weight on the end, and imagine that it's swinging across from one side to the other. So I'll just put some dotted lines here to show where it ends up. Yeah, so what we've got is this pendulum. It's sort of swinging from side to side, and let's imagine that as it swings from side to side, it always reaches the same point. Now we know in reality what will happen is that the swing will get smaller and smaller, and we'll deal with that in the next section. I think it's the next section or a section afterwards, where we'll look at where this motion here, it gets smaller and smaller. Yeah, that's damped harmonic motion, so we'll look at that later. But for now, we're just going to imagine that this keeps moving to the same points either side for an infinite amount of time. So it goes like this. Now imagine that you were looking at this from the top. So let's say that we had a plan view of this type of motion from the top. And then what you would see is this ball at the end of the string moving from side to side. And what you would notice is when it gets to the end parts, it seems to stop instantaneously for a little while and then move towards the centre, past the centre, get to this end point here, again sort of stop, and it would seem to be just moving from side to side like that. We also get the same type of motion with a spring. So again, this is an ideal spring. This is one that we're going to imagine keeps moving forever and ever. So we've got a spring like this, and let's say that the spring goes between being in extension and compression. So this is the same spring. Yeah, and let's say that it moves between these 2 points. So a spring is stretched, it sort of goes back to a bit of compression, then back to being stretched again. And we're going to imagine that it moves between this point and this point, and it moves like this forever and ever. Okay, so in extension, compression, extension, compression. So we're going to get the same type of movement where at these end points here, it seems to be instantaneously at rest before it changes direction. Now the bits we're interested in are this bit in the middle here, which I'm going to call 0. Same here, let's call that 0. And a point halfway between this point here and this point, we'll call that 0. And then the other thing we're interested in are these 2 points that it reaches, these 2 like endpoints just before it changes direction, and I'm going to call that displacement A. So let's take the center of that here and the center of it over here. Yeah, and what we'll do is we'll call the displacement this side A and the displacement this side negative A, because it's going in the other direction. And the same here, we'll call this displacement A, displacement negative A, and the same on this diagram. This displacement will be negative A, and this will be A. Now in all of these diagrams, what's causing the object to go back to the center is an acceleration, and the acceleration always goes towards the center. So we're going to have an acceleration going this way here, an acceleration going this way here, which actually means when this pendulum is at its center point, there is no acceleration. But as soon as it starts to swing the other way, over here, the acceleration is going the opposite direction. It's trying to bring it back to the center point. And again, here, no acceleration, then acceleration towards the center, and it keeps going like this. So the acceleration always points towards the center. It'll be the same on this diagram here. So let's just draw that on. And the same with the spring. The acceleration is towards the center. Now that acceleration, which always points towards its center, so we'll put the acceleration always points toward the center, and this center point can be called the center of oscillation, because the movement that it does is called an oscillation, something that keeps moving from one side to the other continuously. Or it's sometimes referred to as the equilibrium point, because in that center point, that's where the acceleration is zero. So this is called like an equilibrium point. And in real life, these objects want to get back towards equilibrium. So the pendulum wants to end up here in the middle. The spring wants to end up back at its natural length. So also called the equilibrium point. And the acceleration, just write it down, the acceleration is, now I'll use two dots to describe the acceleration. We'll talk about why we can use two dots in a moment. Is negative omega squared x, where omega is what we call the angular velocity. So omega is the angular velocity. Now if you're doing further maths 2 or further mechanics 2, this is one of the topics that you'll be doing in more detail, this angular velocity. Okay, so we've got the Greek letter omega there, squared, which is the angular velocity, times by x, which is the displacement, and it's negative to show that this acceleration is always directed towards the center. So it's always opposite to the direction of motion of the object. So when the pendulum swings out, its acceleration is the opposite direction towards the middle. When it swings out this way, it's towards the middle. The same with the spring. When the spring is an extension, its acceleration is in the opposite direction to the direction it's moving. And when it's being extended out like that, its acceleration is back towards this center point. Okay, so that's why we have a negative there. The acceleration is in the opposite direction to the motion of either the pendulum or the spring or whatever object it is that's exhibiting this simple harmonic motion. Now I spoke about this dot notation and why we use these dots here. Well, whenever we have differentiation with respect to time, we can use this dot notation. So x would be our displacement. Yeah. Now, if we differentiate the displacement with respect to time, we know that's the velocity, but because it's been differentiated with respect to time, we can use this x dot notation rather than writing v. Yes, so that's an option we have. You can write v, but since it's with respect to time, we can write this x with a dot. Often we use that in mechanics. It's the same with the acceleration. The acceleration is the velocity, the differentiation of velocity, again with respect to time. So when it's differentiated with respect to time, we can use the two dots. Another way of writing this is that we're differentiating the displacement twice. Yeah. So we've got the acceleration written as either dv dt or d squared x over dt squared. In simple harmonic motion, the acceleration is negative omega squared x. There's also another way that we can write the acceleration, and that's by using the chain rule. So if we were to use the chain rule, we can write the acceleration, which we know is dv dt. Well, we can split that up. So we have dx dt, okay, which is basically this, isn't it, the velocity, times by, now to make this turn into this, we need to multiply the top by dv and the bottom by dx, so that the x's cancel out here. So now we have another way of writing the acceleration, which is this. So dx dt, that's the velocity. So I've got basically the velocity times by dv dx. So I'll just write that down. Velocity dv dx. So lastly, we're going to look at what a graph of this displacement over time might look like. So let's say that we've got a pendulum starts here, and then it moves across there, it moves across here, it moves across like that. So we can see that as it moves towards the centre, it's going to get faster, and then it's going to slow down, get to its like maximum displacement here, then get faster towards the centre, slow down, get towards that point, and keep repeating that over and over again. And that is actually the graph of sine. That's if we start at the equilibrium point. So let's draw this out. Let's draw a graph of sine and see how this matches up with the diagram. So you've got t on this axis here. We're going to have the displacement on this axis, yeah, on the y-axis there, that's our displacement, and we said that this reaches a maximum displacement of a and a minimum displacement of negative a. This will complete one full cycle, so if it starts here and it goes across here and then back to here, that's one full cycle, or what we call a period, in 2 pi over omega seconds, if we're working in seconds. So I'll just put that down here. This is 2 pi over omega. That's the period time, so I'll just write that down. So period equals 2 pi over omega. So that means that this is going to be pi over omega. This would be 3 pi over 2 omega. And here this will be pi over 2 omega. Yeah, so this angular velocity, if we divide 2 pi by the angular velocity, we get the period, how long it takes to complete one full cycle. Now we can put the acceleration on here. So basically acceleration is going like this. Yeah, back towards that equilibrium, and these are our equilibrium points, or the centre of oscillation here. Here I will write it as centre of oscillation. And lastly, if we write the equation of this sine curve, and this motion here we'd call sinusoidal motion because of the sine graph. You probably already know that from physics. Yeah, if we write the equation in this form, r sine theta, now here theta would be omega t plus alpha. Yeah, so if you write it in that form, then the value of R is going to give you the maximum displacement. It's going to tell you how high and how low the graph goes. So R gives you maximum displacement. R equals max displacement from the center of oscillation. And omega here will give you the number of periods or cycles you get every 2 pi seconds. So for example, if omega is 1, you'll get one of these cycles every 2 pi seconds. If omega was 3, you'd get 3 of these cycles every 2 pi seconds. If omega was, I don't know, 1/5, you'd only get 1/5 of one of these cycles every 2 pi seconds. And alpha here, well, this gives you sort of the displacement on the x-axis. So if, for example, alpha was pi over 2, then our graph would start here. This would be, for example, pi over 2 would be an oscillation that starts at a maximum value, so like maybe a pendulum being pulled over to the side before it's released. So this value here will tell you where in the displacement your oscillation starts. So we gave the example of pi over 2, which means the oscillation starts here. If this was a value of pi, the oscillation starts here, so it's about to move into its like negative displacement phase. If we had a value here of 3 pi over 2, it means we're starting our displacement here on its right at its maximum negative displacement phase. So that's useful to know. So R gives you the maximum displacement because it's going to give you the top and the bottom. Omega gives you the number of periods, the number of cycles you get for every 2 pi seconds. And alpha gives you where the oscillation starts. So here will be at the center of oscillation at the equilibrium point. Here will be at the maximum displacement, and then it's swung round, or here at the minimum displacement. Okay, a particle P moves with simple harmonic motion about a point O. So the point O, that's the center of oscillation, that's our equilibrium point. Given that the maximum displacement of the particle from its center of oscillation is A, we want to show that V squared is equal to this. Okay, so the first thing, we'll write down our equation for simple harmonic motion, which is the acceleration is negative omega squared x. Now, if you look at what we want to get to, we need an equation that has v in it and x in it. And showed you on a previous slide that another way to write the acceleration is v dv dx, and we use the chain rule to derive that. So we can say actually that negative omega squared x is equal to v dv dx. Now we're going to use the separation of variables to deal with this. So that means multiply both sides by dx, and I end up with negative omega squared x dx equals v dv. I can then integrate both sides, with one side, the left hand side, with respect to x, and the right hand side with respect to v, like this. I'll move over this to the other side integral sign because it's a constant, because remember that's the angular velocity and that's going to be a constant for a particular question. So I can put minus omega squared and then integrate x dx and v dv. So let's do that here. So if I do that, I will get negative omega squared times by half x squared equals half v squared plus c. So now I'll times both sides by 2, and then I'll have negative omega squared x squared equals v squared, and I'm timesing my constant by 2, so I'll just give it a different letter. Let's call it d. So this is basically equal to 2c. I shouldn't really put c again because we're basically creating a new constant by timesing that by 2. We're given some information here at the start. At the maximum displacement, the velocity, so given that the maximum displacement from O is A. Now at the maximum displacement, so write this down, at max displacement, that's that part of the cycle when it's instantaneously at rest. So remember the pendulum when it's at those endpoints and it's swinging from side to side. Maximum displacement, momentarily the velocity is 0. So at maximum displacement we have v is 0, and we're told that at that maximum displacement x is a, the displacement is a. So we can now substitute those in to here into our equation to find the value of our constant. So we're subbing in v is 0 and x is a. So that will give us negative omega squared a squared equals, well, v squared is going to be 0 squared plus d. So our constant d is equal to negative omega squared a squared. So if we now put our constant here back into the equation here, we'll have negative omega squared x squared equals v squared plus our constant, which is actually negative omega squared a squared. We'll move the constant over to the other side, so we'll have v squared equals omega squared a squared minus omega squared x squared, and then factorising it we get what's required, which is v squared equals omega squared as a common factor a squared minus x squared as required. Now for part B we want to show that x equals this here, where alpha is a constant. So we start again with our formula. That's the acceleration is negative omega squared x. Now the trick is here is to write this acceleration as what we get when we differentiate the displacement with respect to time twice. Now if we do that, we'll get d squared x over dt squared equals omega squared x, and if I move the, or negative omega x squared, if I move that over to the other side, you may recognize this as a second order differential equation where we would need to solve for x. So if we can solve this second order differential equation in terms of x, that will give us what x is. So that's the trick for this. Write this as d squared x over dt squared, and then we get a second order differential equation in terms of x. So we follow the normal steps for solving a second order differential equation. So the first step is going to be to form the auxiliary equation. So to form the auxiliary equation, we look at the coefficients of each term. So the value of a in an auxiliary equation is going to be 1. The value of b is going to be 0 because we don't have any dx dt terms. And then the coefficient of the x term, c, is going to be omega x. So our auxiliary equation is going to be m squared plus omega squared equals 0. Now if we solve this, we'll get m squared equals negative omega squared. From there we square root both sides, so m will equal plus or minus the square root of negative omega, and that is going to have roots of plus and minus omega I. Okay, so it's got complex roots. Now we know that when a second order differential equation has complex roots, its solution is of this form: e to the px, which is the real part of the complex number p, and then a cos qx plus b sine qx. Now, since we're solving for x in this question, where we have x, we'll actually have t, like this. Q, well, that's going to be omega, here, where we have q. And p, well, there's no real part to our solution to the auxiliary equation, so that's going to be 0, which means this whole e part just becomes 1. So what we'll end up with is this solution: a cos omega t plus b sine omega t, and I should really write here, this is what x equals. So x equals that. So that's our general solution. Now I need to get it into this form, which is like the r sine theta plus alpha form. Now my question doesn't have alpha, it has omega t, so where I have alpha here, where I have theta here, I want to put omega t. Yeah, so you just need to be aware of that. And the way that I'd find r is going to equal, well, the way that we'd get r is that we do Pythagoras on the numbers that were here. So that would be the square root of a squared plus b squared. So just write that down. And tan alpha will be the equal to a over b, or you could say that the alpha equals the tan inverse of a over b. So I'll just write that down. So alpha equals the tan inverse of a over b. So actually we can write this expression here in the form that's required. We just need to say what a is equal to and what alpha would be equal to in terms of a and b. Okay, so I would then write down that x equals this a sine omega t plus alpha, where a equals the square root of a squared plus b squared, that's like my r, and alpha equals the tan inverse of a over b. So we've got the form that they want as required. Okay, so a particle is moving along a straight line at time t seconds. Its displacement from a fixed point is given by this second order differential equation here. Given that at t equals 0, x equals 0, and the particle is moving with velocity t 4, so we'll write that down. When t equals 0, x equals 1, displacement 1. Also, when t equals 0, the velocity is 4. And what we need to do in part A is find an expression for the displacement of the particle after t seconds. That means we want an expression that is x equals something. And we'll get that by solving this second order differential equation. And we just use the normal method to solve that. So this is our second order differential equation. So we're going to bring everything over to one side, like this, so plus 4x equals 0. So the way we're going to solve this is by forming and solving the auxiliary equation. Now, in our auxiliary equation, the coefficients are going to be a equals 1, so that's the coefficient of this. There is no dx dt term, so that means that b equals 0, and the coefficient of the x term is 4, so c equals 4. So our auxiliary equation is going to be m squared plus 4 equals 0. So that's m squared equals negative 4, which is m equals plus or minus 2i. Now we know that when we have complex roots, the general form, and I'm going to write this in terms of t, just as a reminder that we don't put x down but t, it's going to be this. Okay, now our solution has no real part, so that's 0 for p, so all of that just becomes 1. And t, or q, is going to be 2, so we'll have a cos 2t plus sine 2t, or b sine 2t. So let's write that down. So this is our general solution before we found the value of our arbitrary constants. So that will be x equals a cos 2t plus b sine 2t. So now we want to find the value of these constants a and b. Now we're told here we can use this first bit of information in this equation that when t equals 0, x equals 1. So we're going to substitute that in. T equals 0 and x equals 1. So that will give us 1 equals a cos times by 2 times 0 plus b sine 2 times 0. We can work out our value of a. Now, you may be very tempted to say, all right, I'll just write down what cos 0 is or sine 0. But this is the time it's easy to make a mistake. Too many times I'll see students and I'll write cos 0 equals 0. And I'll forget that it equals 1. Just by doing this extra step and writing it out, it just forces you to think carefully about what you're doing. Because it'll be such a shame to get this far and then get your equation wrong and lose a couple of marks because you wrote cos 0 is 0 when it should be 1. And then that'll give you the wrong value for the arbitrary constant, won't it? Because actually what happens is this will become 0, so that's gone. And we'll just end up with a equal, or 1 equals a times 1, so a equals 1. Okay, now we want to find the value of b. Now the other bit of information is when t equals 0, v equals 4. So we need to find an equation for v. That means differentiating this, yeah? So v is equal to dx dt, and that will be equal to, well, cos 2t differentiated will become minus 2 sine 2t. So minus 2a sine 2t, and then sine 2t differentiate will become 2 cos 2t. So plus 2b cos 2t. So from there we will substitute in t equals 0, v equals 4. So we'll have 4 equals negative 2. Now a we've worked out as 1 times by sine 2 times 0 plus 2b cos 2 times 0. So all of this part goes cosine 0, 0, just leaving 2b equals 4. So b equals 2. So we have the value of our arbitrary constants to give the particular solution, which will be x equals a cos 2t, or 1 times by cos 2t, plus b, which is 2 sine 2t. Then part b asks us to hence determine the maximum displacement of the particle from O. So we are going to use our part A answer to help us work out the maximum displacement. Now we'll get the maximum displacement by writing this in the form r cos theta plus alpha. So r sine theta plus alpha. Now theta here is 2t plus alpha. The way that we find r is going to be equal to the square root of a squared plus b squared. So that's the square root of 1 squared plus 2 squared, which is root 5. And we actually don't need to find alpha to find a maximum displacement, but we'll work out anyway. Alpha is going to equal the tan inverse of a over b, so that's going to be the tan inverse of a half. Now this needs to be in radians, since remember one cycle is in 2 pi, so we're measuring our time in units of 2 pi in radians, okay? Since 1 period equals 2 pi, that's why we're using radians, and we'll use radians whenever we have this simple harmonic motion. So that will give a value of alpha as 0.4636, so we'll give that to 3 significant figures, so 0.464, 0.464, I'll just put 3 significant figures. So that means that actually this that we've got written there can be written as root 5 sine 2t plus 0.464. Okay, now I'll highlight that. That isn't our final answer, but we will use that to get the final answer by highlighting it rather than colouring it in yellow, like this. And it's going to be the value of r that gives us the maximum displacement. So that's root 5. So we'll leave it in that form. Now remember, these are SI units, so time is going to be seconds, and this will be meters. So all right, max, whoops, be better in a pen we can see, max displacement equals root 5 meters. Now that will be our final answer, but it's worth pointing out actually what other things this equation is telling us about the motion of this particle. Well, the 2 here tells us that there are 2 periods, there are 2 cycles for every 2 pi seconds. Yeah, so there'll be 2 periods, 2 cycles for every 2 pi seconds. And also, this particle starts at a displacement from equilibrium, from the center of oscillation of 0.464 meters. So it doesn't start at its maximum displacement. So I'm guessing the square root of 5 isn't 0.464. I'm just checking, no, it's 2.23. So it's starting not at the center point, but somewhere off center as a positive displacement of just under half a meter. And then it will then swing to its maximum displacement, or move to its maximum displacement of root 5, and it will keep doing that in this simple harmonic motion. Okay, so we've got a particle here is attached to the ends of 2 identical springs. And let's just underline that, 2 identical springs. The free ends of the springs are attached to 2 points A and B. Point C lies in between A and B such that ABC is a straight line and AC does not equal BC. The particle is held at C and then released from rest. At time t seconds, the displacement of the particle from C is x meters and its velocity is v meters per second. The subsequent motion of the particle can be described by this differential equation here, which I'm guessing we'll solve in a minute. Describe the motion of the particle. So I'm just going to draw a diagram so you can get your head around what's going on here. So we've got a fixed point here, we've got a fixed point here. This diagram isn't really necessary really, but so you can get your head around it. We've got a particle P, so let's call this P here, like that, and there are 2 identical springs, so I'm going to try and draw 2 identical springs like this. Okay, and one end of the spring here is A, one end here is B, and C is somewhere here. Now notice that the distances here are not the same. So this is off center. It's released from rest. Now what's going to happen? It's going to bounce between the two, isn't it? This spring is going to pull it that way. Then when this one is an extension, it's going to pull it back that way. So we've got here simple harmonic motion. Now we know in reality it will be damped, which we do in the next section, which means it will slow down to nothing. But we're just going to pretend it's going to keep going like that forever. So if we're going to describe the motion of the particle, it is simple harmonic motion. On to part B, it says given that x equals 0.4 and v equals 0 and t equals 0, solve the differential equation to find x as a function of t. So remember, these are what we call boundary conditions. Boundary conditions. And if we're going to solve the differential equation, which is x double dot equals negative 25x, we'll write it as a second order differential equation. So x double dot we'll write as d squared x over dt squared, like this. Then we'll add the 25x to both sides. Okay, now we're going to solve the auxiliary equation. So with our auxiliary equation, we are going to have a equal to 1, b equal to 0, and c equal to 25. So the auxiliary equation is going to be m squared plus 25 equals 0, which is m squared equals negative 25. So m is going to be plus or minus 5i. So we know that the equation is going to be of this form: e to the pt, remember to use the letter t, a cos qt plus b sine qt. I suppose qt because this question is such a qt. Anyway, right, so what does that give us for our general solution? So that's going to be x equals, now q is 5, isn't it? So a cos 5t plus b sine 5t. Right, so now let's use our boundary conditions. And the first boundary condition we're going to use is x equals 0.4 when t is 0. So we'll substitute those in and we'll get 0.4 equals. Now, this bit we could do in our head if we're careful. Actually, no, let me write it all out. I don't want to take any chances. A cos 5 times 0 plus b sine 5 times 0. When we take chances, what happens? Could make a mistake. Right, now, cos of 0 is 1. Cos of 0 is, sorry, sine of 0 is 0. So that's all gone. What does that leave? That will leave a equals 0.4. So that's our first one. A equals 0.4. Now to find the value of v, if we're going to use the other boundary conditions, v equals 0, t equals 0, we need to differentiate this to find v. So v is equal to dx dt, and dx dt is equal to negative 5a sine 5t. So I'm differentiating that first term, and then plus 5b, because I almost wrote just b there, plus 5b cos 5t. Now we'll put in our boundary conditions, because that's what v equals, and they are v equals 0 when t equals 0. So I will have 0, which is v, equals negative 5a. Now we worked out a, didn't we? A is 0.4, so let's put 0.4 there. Sine 5 times 0 plus 5b cos 5 times 0. So all of this bit here goes, cosine 0 is 0, just leaving 0 equals 5b, because that's 1, so that means that b equals 0. So our particular solution, once we've used our boundary conditions, is x equals, a was 0.4, so 0.4 cos 5t, and there is no sine part because that was 0, wasn't it? Okay, so there we go, we've answered part A. There's our differential equation. We solve the differential equation to find x as a function of t. Okay, now for part C, it asks us to find the period of motion and calculate the maximum speed of p. So the first thing is that, part C, not part B, the period of the motion we get from here. Now remember, this tells us how many cycles there are in 2 pi seconds. So whatever this number is gives us the number of cycles. So if we do 2 pi divided by 5, that will give us the how long each period is. Okay, so a period is basically 2 pi over 5. Yeah, and that will be seconds. So yeah, so whatever that number is, 2 pi divided by that gives us the length of the period. Then the maximum speed, well, we know that at max speed, the acceleration equals 0. So if we go back to our original equation for acceleration, so I suppose we could use this one here. If acceleration equals 0, that means x equals 0. Now that's interesting. What that basically means is that the maximum speed occurs at the center of oscillation in this particular case. So max speed is at center of oscillation, because center of oscillation will be when x equals 0, and I think generally that's the case when you've got simple harmonic motion, that when the object, the pendulum or the spring, reaches this center point, that's when the maximum velocity occurs, because either side of it, it's slowing down because the acceleration is pointing back towards the middle. Yeah, so remember, we have these accelerations here. So yeah, it's definitely the maximum speed at center of oscillation. Right, so if we put 0 into this equation to work out at what time the maximum speed occurs, and then we can put that into here to work out the maximum speed. Right, so that will give us 0.4 cos 5t equals 0, which will give us cos 5t equals 0. So that means that 5t, well, there's many values. We just need to do the cos inverse of 0. So that will give us 5t pi over 2, or 3 pi over 2, or 5 pi over 2, and so on. Yeah, so we just need the first one. This is where the maximum speeds are going to occur. So that means that t, we divide those by 5, so I'll have pi over 10, 3 pi over 10, etc. So we substitute that value of t into v here. So the maximum speed will be minus 5 times by a, which is 0.4, times by the sine of 5 times t. Well, that's basically that pi over 2, or whatever value we choose. So we'll get a maximum value of -2 meters per second. That's the velocity. Now it's asking for the speed, so the speed will just be the modulus of that. So 2 meters per second, we just take the positive value, so we'll take that there as our final answer. So you should now be able to do exercise 8b on pages 178 to 180 of the textbook. So remember, this section's all been about this simple harmonic motion. So I gave this example of this pendulum swinging from one side to the other. So here down the middle we would have what we call our center of oscillation. Center of oscillation. And in the center of oscillation we found that this is where we get our maximum velocity in the center here. At these end points, this is where v or v would be equal to 0 momentarily. And then here at the center here, this is where a would be equal to 0 and a maximum velocity. The displacement, if we give it in terms of a, we call that a, we'll call this negative a, this displacement from the center. And it's often really useful if we write our equation in the form r sine omega t plus alpha, because this will give you, or if we do 2 pi divided by omega, we get the period length in seconds, and this value of r here, this will give us the maximum displacement value of r. And also with this simple harmonic motion, the acceleration is towards the center, and that's omega squared x, where omega is what we call the angular velocity. And the acceleration is always negative, so that's why we have this, because it's always opposite to the direction of motion. So remember, we can also write the acceleration as this, dv dt, or even d squared x over dt squared, or even as v dv dx if we're using a chain rule.